Hello, welcome to Cosmic Veil. This is our quiet observatory where deep curiosity meets calm, and the science of the stars rocks you to sleep. Before you and I open the dome tonight. As an astronomer, I always wonder where you're looking up from and what time it is there right now. Drop a note in the comments below. I am constantly amazed by how many fellow stargazers drift into this space from entirely different time zones. If you enjoy tonight's observations, consider giving this video a gentle like and subscribing to the channel so you never miss a night under the lens. It helps more sleepy minds find our telescope. Now, the data we are exploring tonight is beautiful. We're tracking how galaxies, vast cities of stars, are born from sheer darkness and dust. I just hope my passion for it won't keep you awake. But if it does, at least you will have some solid astrophysics for your morning coffee. So get comfortable at the eyepiece. Let your shoulders drop, breathe slowly. We are tracking back 13.8 billion years of cosmic history tonight, no rush. The stars always wait for us. Let us begin. 13.8 billion years ago, everything was small. Not just small like the cramped control room of an old telescope, but impossibly, unimaginably compact. Hotter than any stellar core I have ever measured, and denser than a lab notebook. Then, in a single moment that still puzzles my colleagues. It began, not an explosion, despite what the textbooks name it. The Big Bang was actually a rapid, beautifully graceful swelling. Space itself expanded outward across every single direction. Faster than light speed itself, like a weather balloon filling in a massive gale, there was absolutely no debris flying through empty space. Space itself was the debris, simply generating itself as it expanded. In those first fleeting microseconds, our models show the universe as a seething soup of fundamental particles. Quarks slammed into gluons, trapped photons zipped around madly, and gravity quietly started taking notes. It was pure chaos, blindingly hot and impossible to observe. Not exactly a great spot for pitching a telescope just yet. But our calculations show this chaotic era held infinite potential. Hydrogen and helium, the absolute lightest elements, formed like tiny building blocks, snapping together right out of the heat. These simple atoms would eventually go on to construct everything. Every star we track, planets, people, and of course, galaxies. Roughly 380,000 years after the Bang, a tiny fraction of cosmic time, something stunning appeared. Temperatures finally dropped enough for those atoms to trap electrons, creating the very first neutral atoms. Light, which had been bouncing around in the dense fog like a trapped firefly, was finally free to travel. We call this moment recombination. It created the cosmic microwave background, a faint thermal afterglow that my radio dishes still pick up today. If we could see microwaves natively, the entire night sky would glow bright with that ancient fire. But even with all that background radiation, no stars existed. Not quite yet, our telescopes would have seen only a massive, dark, expanding cloud of pure gas. If you and I could drift through it together, we'd detect only subtle thermal ripples, tiny irregularities in an otherwise smooth void. Those tiny ripples meant everything. They were physical echoes of quantum fluctuations from the very start, stretched wide by cosmic inflation. A few random regions were just a fraction denser than others. Barely measurable on a spectrograph, but gravity noticed, and gravity never forgets. Over millions of years, those dense pockets of gas began pulling in more mass, slowly, silently gathering together, like condensation forming on a cold telescope lens. These gas clumps, the very seeds of future galaxies, were completely invisible to optical sensors. If eyes had even existed then, yet they were slowly setting up the spectacular celestial drama we study today. As an astronomer, I find it strange to imagine a dark, quiet universe, but it was. No starlight, no bright galaxies, just the silent, heavy math of matter collapsing inward. A massive era of stillness before the storm, a deep cosmic breath in, right before the universe finally exhaled starlight. Yet even today, armed with space telescopes and complex physics, my colleagues and I are still decoding the timeline. How did those tiny gas clumps forge the massive, sweeping arms of spiral galaxies? Why did some sectors ignite into brilliant stellar nurseries, while others faded into massive, empty voids? The raw data is written out there, glowing in every distant nebula and ancient star cluster. You and I just need to keep looking up, so the universe expanded. Dark matter, that invisible skeleton we can only measure through gravity, began shaping the cosmic web. Hydrogen stretched into long filaments. Gravity gave the order and the cosmos followed. Soon, the very first stars would spark to life. The shadows would end, but for now, the cosmic stage was set. To us astronomers, the universe wasn't just expanding anymore, it was awakening. Starlight hadn't arrived yet, the galaxies still slept. For hundreds of millions of years, the cosmos stayed hidden in what you and I call the cosmic dark ages. Despite that gloomy title, you won't find any medieval castles out here. No dragons either, unless you count massive beasts made of raw hydrogen plasma. I look back at this pure darkness, a universe heavy with matter, void of light. After the Big Bang's brilliant flash and the fading microwave background, deep space fell perfectly silent. Neutral hydrogen gas blanketed everything like a vast, unseen fog. My telescope would find no stars shining through it, no distant galaxies twinkling yet. The cosmos went completely dim, not from a lack of energy, but because it just hadn't figured out how to ignite the lights. Imagine floating through this era, an endlessly stretching sea of chilled hydrogen and helium gas, where lonely electrons drift past like quiet jellyfish. We know gravity was pulling ever so gently on that gas. It formed scattered clouds, though everything shifted at a glacial pace. Not that time mattered much. 0 clocks, 0 sunrises, just the slow, patient gathering of mass across an early universe that simply wasn't in a hurry. Yet something incredible was quietly taking shape. In this shadowy silence, the exact cosmic foundation I study today was being built. You see, during cosmic inflation, that lightning-fast burst right after the Big Bang. Microscopic quantum ripples stretched across the void. These tiny density bumps wouldn't look like much through a lens, but gravity certainly noticed them. Wherever the cosmic matter was slightly thicker, it started pulling more of itself inward. Over hundreds of millions of years, those ripples matured into giant tendrils and knots, what my colleagues call the cosmic web. Let's picture the universe together as a massive sponge, a vast spiderweb woven by glowing filaments of primordial gas and dark matter. These grand threads are exactly where future galaxies would anchor, tugged into position by gravity's steady hand. Between them lay the voids, giant, lonely stretches of near absolute nothingness, where our observatories will rarely find a single star. Anchoring it all was a silent partner we track today. Dark matter, it never glows. It never reflects, and it completely ignores light. That makes it famously difficult for us to measure, and frankly, terrible at parties. But this invisible mass was vital. Its gravitational pull built the grand scaffolding of the cosmos, dragging ordinary matter, sweeping up hydrogen and helium gas, acting like the hidden frame behind a masterpiece. Without dark matter anchoring things, our night sky might have stayed foggy forever. Now, if you and I are still stargazing tonight, you might be wondering the same thing astronomers ask. Why did the very first stars take so long to ignite? Well, forging a star isn't quite as simple as tossing gas into a cosmic blender and flipping a switch. Hydrogen had to gather into incredibly dense pockets for gravity to win, crushing it until core temperatures hit millions of degrees. Only then could nuclear fusion trigger the stellar dance we see today, but the infant cosmos was taking its sweet time. It let gravity sculpt at its own quiet pace, slowly molding the loose gas into heavily packed cosmic clouds. Very patiently, these massive nebulae collapsed inward under their own sheer weight. Deep inside one of those dense knots, a spark was brewing. A single point of starlight piercing the dark space. When that finally happened, our entire universe shifted. But right here inside this endless, quiet interlude, the universe was merely drawing a deep breath. Just like an orchestra tuning up before a symphony, the raw elements sat waiting. The celestial music hadn't started yet. 0 galaxies, 0 stars, just a building tension, a deep sense that profound beauty was coming. For us astronomers, that's incredibly comforting. Even in pitch black, the cosmos was never entirely still. Beneath that silence, it was dreaming, structuring itself, preparing to shine. Dawn was approaching, and then it finally broke. Somewhere inside a collapsing pocket of primal hydrogen, gravity squeezed perfectly tight. Right at the core of that unseen celestial swirl, internal pressure skyrocketed. and temperatures violently spiked to millions of degrees. Simple atoms were forced so close together that their fundamental nature forever changed. And right then, quietly and without any fanfare, the very first star was born. The first real light since the Big Bang. Now, these weren't normal suns. We call them population 3 stars, wildly different from today's night sky. They were gargantuan, highly unstable, and blazing hot, forged inside the absolute purest conditions the cosmos will ever experience. 0 heavy elements existed back then, no carbon, oxygen, or iron. Just pure hydrogen, helium, and a dusting of lithium left from the Big Bang. That made these ancient giants burn much fiercer than our sun. We calculate some were hundreds of times more massive than our sun, living incredibly short. Furious lives before collapsing into black holes or detonating as brilliant supernovas. If you and I floated near them, honestly, we would be scorched. We would watch these first stars ignite deep space like bonfires in a vast forest. One by one, their starlight pierced through the thick hydrogen fog that had choked our universe since the very beginning. Slowly, that long darkness lifted. In my field, we call this era cosmic reionization. While that sounds like a plot from an old science fiction movie, for those of us studying it, it was a peaceful, dramatic shift. Ultraviolet radiation from those infant suns began stripping electrons off the neutral hydrogen gas around them. This ionized space, making the universe completely transparent. To an astrophysicist, it looks as though someone finally cracked open the shutters of a dark greenhouse, letting light flood inside. Sitting at our observatories, billions of years later, I cannot observe these first stars directly. Their lives were much too brief, terribly distant, and their ancient light too faint. But we find their fingerprints everywhere. They completely transformed our cosmos from freezing and dark into something warm and glowing. They scattered the very first heavy elements across deep space. The vital ingredients for anything heavier than hydrogen. That includes you, me, and the hot tea sitting on my desk tonight. I like to think these stars were early artists, sketching faint galaxy outlines on the dark canvas of space. But true galaxies had not formed yet. Not just yet. My data shows these early stars scattered in tiny clusters, pulled by gravity, but missing the grand, swirling stellar cities I observe in tonight's sky. They were humble villages, proto-galaxies testing the cosmic waters of structure and pull, but the right chemical ingredients were finally gathering. When those giant stars met their end in violent supernovas, they blasted rich, heavy metals deep into the surrounding gas clouds. Those enriched clouds cooled efficiently, collapsing much faster to forge fresh stars with incredible ease. The next stellar generation, what astronomers call population 2, started emerging. They were smaller, much more stable. And somehow deeply familiar, this sparked the great cosmic engine. Gravity simply pulls in cold gas. New suns ignite, they burn, perish, and fling their enriched cores outward, letting countless more stars take shape. Every new generation builds on ashes of the previous, layering heavy matter like deep stardust sediment. You and I might wonder, how do my colleagues know this happened if we never captured those ancient stars? The truth hides in faint light patterns, like ghostly smudges left on a telescope lens, by analyzing the oldest galaxies and deep chemical signatures. Alongside the fading cosmic microwave background, researchers like me can map out the early childhood of space in stunning detail. It is exactly like recreating the history of a vast forest by examining its oldest timber, the soil, and subtle wind patterns. The signals are faint, but we always find them. Recently, we started catching real glimpses. Using massive observatories like the James Webb Telescope, we are finally watching early galaxies form. They appear as tiny, chaotic, glowing clusters of stars from a mere few hundred million years after the Big Bang. I am peering into the deep nursery where early light first bloomed. It is truly humbling. Those distant stars burned out long before our solar system was even a quiet dream. Their dim light traveled across the void for billions of years, slipping past colliding galaxies and massive wandering black holes, passing our growing Milky Way, until it finally landed softly on the golden mirrors of my telescope aimed at the dark. And now you and I share that light, resting in your mind as you drift towards sleep. The cosmos, once completely dark, sparked its first lanterns. That primordial night was over, and the age of galaxies was about to begin. Space was glowing now, not with blinding brilliance, but more like the first soft hint of dawn on a freezing morning. The stars arrived, their light unraveling the deep fog, gently warming the complete silence. But my models show them scattered and isolated, flickering like distant campfires. No cities, no roads, just lonely pockets of light suspended in an endless void. Gravity, however, had different plans. Those distant stars were not just floating aimlessly. They were pulled together by invisible, heavy threads. Everywhere I looked, or rather, everywhere an ultraviolet sensor would look if it had infinite patience, tiny clusters of stars were slowly converging together in the dark. Gravity was silently weaving them into massive structures. The quiet stellar villages were becoming towns, and those towns would become bustling cities. These early cities, these proto-galaxies, were the rough first drafts of the star systems I study today. It never happened perfectly. There were no neat blueprints, no engineers measuring out spiral arms with precise rulers. It was absolute chaos. Clumps collided, merged, tore each other entirely apart, and fused again. The early universe was a rough neighborhood to observe. Through our telescopes, we see gas clouds crash, stars tossed from one group to another. We observe some early galaxies forming fast, gorging on nearby gas and swallowing neighbors. Others simply stalled, stranded in quiet space pockets like lonely cosmic wallflowers. Back then, they didn't resemble the elegant spirals or massive ellipticals I usually capture in my glossy telescope images. They were messy, chaotic, unrefined. They looked more like cosmic blobs than the symmetrical beauties we search for today. Yet, inside that chaos, they grew. Over time, I see their shapes stabilize, gently nudged by gravity and sculpted by space. We know much of this early architecture was guided by something on a massive scale. The cosmic web, you and I can picture it as a vast, three-dimensional lace woven across the universe. Dense knots where threads of dark matter crossed became the main hubs. In my maps, these are regions where galaxies clustered like seeds in rich soil. Long tendrils stretched between them, pulling galaxies along invisible gravity rails. Between these threads lie vast voids, eerie and quiet, where I rarely find any galaxies. It is inside these dense cosmic intersections that early proto-galaxies had everything to gain and to fear. When we observe so much gas and gravity crammed together, things tend to get quite dramatic. Galaxies smashed into one another, a slow-motion cosmic dance taking hundreds of millions of years. These were not violent collisions like you might assume. Stars sit so far apart that almost none actually hit each other. But their massive gravitational fields tangled. Extreme tidal forces twisted these galaxies into bizarre shapes. Streams of stars stretched like taffy, trailing far behind their original galactic homes. Gas clouds collided, compressing fiercely to spark new waves of creation. We romantically call these starbursts. Amid this deep space chaos, brand new stars bloomed. Fresh clusters formed. Over deep time, what was a shapeless clump finally began resembling something quite familiar. What sets a galaxy's final shape? You and I are still trying to answer that. We do know this: undisturbed galaxies with the perfect amount of spin could eventually flatten out, becoming elegant, spinning spirals just like our very own Milky Way. Others, battered by collisions in crowded cosmic neighborhoods, evolved into ellipticals. Those are round, puffy collections of ancient stars. And some galaxies simply never managed to settle down. Forever lopsided and patchy. In my field, we call them irregular galaxies, and frankly, I love their chaotic energy. Yet even in that irregularity, these galaxies became something totally new, something lasting. They acted as massive star forges, where gravity and deep space gas ignited pure creation. Deep inside, stars were born, lived, and died. They scattered carbon, oxygen, and iron ashes into the interstellar medium, enriching the cosmos for future generations. Over billions of years, recycling this ancient stardust slowly built planets, moons, thick atmospheres, and eventually, at least once, a small blue globe where I would sit tonight, whispering these exact stories into a microphone. When I peer through the lens, it is easy to forget how long galaxies spend shaping themselves. The starlight we study today comes from second, third, or fourth generation creations, forged entirely from the cold remains of dead ancestors. Think of galaxies as the family albums of our universe. Every star a page, every nebula a chapter waiting to be written. As these galaxies matured, they built vast communities, rich clusters, tight groups, and massive superclusters. Much like stars gathering together, the galaxies themselves are rarely solitary wanderers. They orbit each other, influence each other, and often fall gracefully into a partner's cosmic embrace over deep eons. Our very own Milky Way resides in one, a quiet little neighborhood we call the local group. Here it shares the dark with Andromeda, the Triangulum galaxy, and dozens of smaller companions. But that is a story for another night. Back then, our universe crossed a major milestone. It was no longer a random sea of gas and light. It became fully structured. It developed complexity. It built sprawling neighborhoods. Stars finally found permanent homes, and the cosmos started organizing its own raw brilliance. By this era, the early universe was far from empty. Deep space galaxies had formed, some shy and dense, others sprawling and incredibly dramatic. Stars traced massive orbits. Gas clouds shimmered with newborn light. The endless dark had not completely vanished, but it receded. It pulled back like a velvet curtain, revealing the absolute grand stage of creation. And out on that stage, galaxies started taking shape, but as we know, they are rarely uniform. They appear in so many different shapes and sizes, exactly like snowflakes. Well, if snowflakes weighed a few 100 billion suns, some spin elegantly like silver pinwheels frozen in space. Through my telescope, others look squat and round, like celestial dumplings, and a few honestly look like someone tried drawing a star system from memory while riding a roller coaster. Let's explore this together. Why do some spin into spirals while others become elliptical or completely irregular? For us astronomers, the answer is always time, deep space gravity, and immense cosmic patience. I always start observing the spirals, the absolute show-offs of deep space. These spiraling star cities are easily the most stunning sights I photograph. They are the ones printed on classroom posters or shown in astronomy documentaries where soaring violins play. With their graceful, glowing arms and bright cores, I see them as cosmic hurricanes caught mid-swirl. Even our own Milky Way is a classic spiral. Our solar system rests inside one of those arms, a quiet suburban speck bordering a massive rotating city. Spirals hold massive amounts of interstellar gas and dust, the perfect fuel for newborn stars. Through my lens, those young stars light up the arms like bright fairy lights against the dark. A spiral's entire structure depends on constant motion. When an early galaxy holds a healthy amount of spin, meaning its cosmic dust and stars rotate in a somewhat orderly way, the gravity naturally flattens it out. As epochs pass, gravity waves ripple across that disk, squeezing gas together and igniting stars. Suddenly, bright spiral arms appear. They are not solid structures, just flowing patterns moving through the void like traffic jams. Individual stars drift in and out, but the pattern remains. Of course, my field notes show not every galaxy stays elegant. I often study elliptical galaxies next. They are older, rounder, and far more relaxed, lacking any sweeping arms. Instead, they look like giant glowing clouds, shaped like soft spheres or stretched out footballs. Through my filters, they glow with older, redder stars, holding very little gas for new ones. If spirals are busy cities, I call ellipticals the sleepy retirement communities of deep space. Quiet, perfectly stable, unchanging. We believe ellipticals form during massive galactic mergers. When two equal-sized spirals crash together, that beautiful, orderly spin gets totally destroyed. Billions of suns are flung into wild orbits. The raw gas burns away, leaving behind nothing but a huge, glowing, shapeless mass. It is dramatic, chaotic, and strangely beautiful. Exactly like smashing two glass snow globes together in a vacuum, waiting for flakes to settle. Then I find the irregular galaxies, the ones defying every classification rule we have, absolute cosmic oddballs and strange nonconformists. Some are mere infants, lacking the time to build a shape. Others are ancient systems that wandered too close to a massive neighbor, their stars stretched completely out of alignment by violent gravity. On my screen, they look like paint splatters, but they are actually bursting with frantic star formation and raw cosmic energy. Many targets fall perfectly between our strict categories. Spirals holding heavy centers, ellipticals wearing rings, odd hybrid anomalies. Mapping the cosmos, like everything in observational astronomy, is just as messy as the universe itself. But stick with me here, we still categorize them to make sense of the deep night sky. And for us, a galaxy's shape means far more than just visual beauty. It reveals a deeply fundamental truth about a system's history. When I spot a spiral, I know it enjoyed a calm youth. Steady gas flow, minor collisions, nothing terribly traumatic. But an elliptical shape tells me it survived a massive battle, shaped by ancient, violent cosmic collisions, and the irregulars. Well, my data says they are either newborn, unlucky, or both. The truly fascinating part is watching them slowly morph even today. Beautiful spirals collapse into ellipticals. Tiny dwarf systems crash together to forge towering giants. Invisible gravity constantly tugs at their spiral arms, twists their glowing cores, and scatters suns. I have learned nothing out there is static, especially not something as alive as a galaxy. My colleagues and I used the Hubble Space Telescope to finally reveal this cosmic diversity. With it, we photograph star systems across all life stages, from tiny early universe clusters to majestic local spirals and heavy ancient ellipticals. I have watched distant galaxies violently collide, stretch, tear apart, and slowly rebuild themselves from the heavy wreckage. Every single cluster tells me a story, and often that history is purely written in its physical shape. So the next time you and I view a deep space image, whether it is a perfect blue spiral, a glowing elliptical halo, or a chaotic star clump, remember we are staring at billions of years of history. A long record of gravity and light, of massive stars born, aged, and gone. Of interstellar clouds drifting, violently colliding, and forging something new. Up here, galaxies do not just shine, they remember. Let's bring it home for a minute. You and I have been floating through deep space, watching stars ignite and beautiful galaxies take shape. But now it is time to return to our own quiet cosmic neighborhood. It feels deeply familiar, not because I've seen it from the outside, though we try, but because it holds every sunrise, every breath, and every human memory. Our home is the Milky Way galaxy. And she is a stunning host. From my observatory, sitting right inside her, I cannot see the whole shape. It is just like trying to read the label from inside the bottle. What I do see through the dome, far away from city lights, is a glowing river of starlight painted straight across the dark sky. That shimmering band of dust and light is our view across the galactic plane. I am looking straight through billions of stars. We live in a massive spiral galaxy, stretching about 100,000 light-years across. It holds roughly 1 to 400 billion bright stars. Why such a huge guess? Because counting stars through a telescope is tough when you sit inside a thick cloud of cosmic dust with endless patience. Still, my best astronomical estimates put us about a third of the way out in the Orion Arm. We are cosmic suburbanites, sitting safely away from the chaotic center. That galactic core is a wild, intensely energetic zone. It holds a supermassive black hole we call Sagittarius A. A pure gravitational beast roughly 4 million times the mass of our Sun. It is a quiet eater, not the brightest object, but it anchors our entire galaxy together. I watch stars whip around it in dizzying loops, like moths circling an unseen fire. My colleagues and I cannot see it directly. We only know it exists by how it bends its surroundings. Picture watching giant stars trapped and spinning in a dark, invisible whirlpool. I have tracked their paths for years, and the data is undeniable. Something deeply massive, incredibly dense, and forever hungry sits right at the galactic core. But do not worry, it will not be swallowing Earth anytime soon. Our galaxy did not always look this perfect. Like most star systems, it holds a long, violently beautiful past. Over billions of years, it formed through brutal cosmic mergers and galactic acquisitions. Smaller star clusters were dragged in, consumed, and folded into the spiral arms. Through my lenses, I see those devoured stars lingering in the outer halo, looping like lost ghosts from forgotten homes. And the feast continues. Even as we speak, our galaxy is tearing apart a few smaller neighbors. The Sagittarius dwarf galaxy, for example, is currently being shredded and absorbed. It looks peaceful enough on a human time scale, but stretch that over millions of years. And it is like watching dark ink slowly bled into a quiet pool. More dramatically, my calculations show we are on a slow collision course with our biggest neighbor, the Andromeda Galaxy. At 2.5 million light-years out, it rushes toward us at 110 kilometers per second. Do not panic, you have 4 billion years to prepare, and it will not actually end our world. The two spirals will simply merge into a brand new, giant elliptical star system. Some of my peers call the future galaxy Milkomeda. Honestly, it sounds like cheap space yogurt, but we accept it. Stick with me here. It is astonishing we figured all this out from deep inside the galaxy. Through huge radio telescopes and infrared data. And brilliant math, we managed to trace the spiral arms and map the ancient stars. Simulating its entire birth and future, I'm basically solving a jigsaw puzzle from the inside out, finding the final picture absolutely huge. And beneath all that chaos, our tiny yellow sun just keeps quietly orbiting. My charts show it takes about 225 million years to finish a single lap around the core. That means we have only completed roughly 20 full trips since our solar system formed. Think about that, the last time Earth drifted through this exact spot, dinosaurs were just waking up. I measure galactic years not in birthdays, but in sweeping planetary epochs. So here we sit, spinning silently in the dark arms. A pale blue dot orbiting a normal yellow star, totally bathed in the soft glow of a billion suns. Every single atom in your body was cooked inside massive stars that burned out long before us. Deep in galaxies swallowed by our own, you and I are quite literally written into the Milky Way. I see us as a moving, breathing piece of galactic history, star stuff listening to starlight. The galaxy isn't just up there, you carry it inside you. If galaxies are the grand cities of the cosmos, I always wonder what built them. Who or what poured those invisible foundations, keeping billions of stars perfectly spinning in place, and making sure they do not drift apart like dandelion seeds. You and I are about to meet 3 unlikely cosmic architects, quietly working since the very beginning. Gravity, dark matter, and black holes, maybe not the most charming trio in astrophysics. They do not glow or sing or get invited to parties. Yet without my favorite 3 forces, our universe would be a very empty, completely formless place. Let us start with gravity. It is the oldest and most familiar force we study. I call gravity the great gatherer. It never makes a fuss or shouts, it simply pulls. It always has and it always will. Deep in the early universe, as everything expanded from the Big Bang, gravity was the sole reason matter began to clump. It caught those tiny little ripples in the density of space, the absolute faintest wrinkles, and amplified them. It drew gas and dark matter together until the first stars and galaxies finally formed. Gravity is slow, patient, and never rests, but here is the catch I teach my students. Gravity is not actually very strong. It is actually the absolute weakest of the 4 fundamental forces in physics. Drop a paperclip, and gravity pulls it right to the floor. But hold a magnet above it, and that paperclip suddenly defies gravity with total ease. A tiny magnetic field beats an entire planet's gravitational pull. So why does it shape the deep cosmos? Simple. Gravity always accumulates over time. It never cancels out the way electric or magnetic forces do. Out there, the more mass a star has, the more gravity it gets. And across the vast, freezing emptiness of space, with zero friction or air resistance, that quiet persistence really adds up. But even with gravity, my colleagues and I hit a mystery. Something was missing when we peered into galaxies. When we actually measured how fast those outer stars were spinning, we found something bizarre. Those outer stars, sitting way out on the galactic edge, were moving much too fast. Based on the visible mass I could measure, they should have been flung out into deep space like glitter off a spinning wheel, but they held on. They stayed totally loyal, orderly, and stable. That mathematically broke our models, unless there was somehow much more mass out there. A whole lot more entered dark matter, an invisible ghost we cannot see, cannot touch, cannot interact with, yet I know it exists because its heavy gravitational fingerprints cover the entire observable universe. Dark matter completely ignores light. It casts no glow through our telescopes, but it certainly pulls. And there is a staggering amount of it, roughly 5 times more dark matter by mass than regular matter. For every single star or glowing gas cloud I map, there is a giant, invisible halo of dark matter gripping everything tightly together. Picture the galaxy as a glowing jellyfish, swimming peacefully inside a massive, invisible ocean bubble. That invisible bubble is the dark matter halo, keeping our jellyfish from shredding apart. Without it, the spiral galaxies we observe simply could not exist. They never would have formed to begin with, and if they magically did, they would instantly dissolve. Billions of stars would fly away in all directions. The beautiful, sweeping spiral arms I photograph would never survive. Honestly, we astronomers still do not know exactly what it is. I read new theories daily, exotic particles, supersymmetric partners, even wild ideas about extra dimensions. None are proven, yet its heavy pull is completely undeniable. Like wind sweeping the ocean, I do not need to see it directly to know it is there. Now stick with me here, as if galaxies lacked secrets, we reach our final cosmic actor, black holes. And I mean true monsters, supermassive black holes. These sleeping giants sit waiting at the center of nearly every large galaxy I study, including our own. They weigh anywhere from millions to literally billions of times the mass of our sun, and while pop culture treats them as purely destructive voids, I view them as galactic administrators, deeply quiet, mysterious, and highly influential. In the old days, astronomers thought these supermassive black holes were just passive passengers, accidental heavyweights in the galactic core. But over my career, our telescopes revealed they are truly the co-authors of a galaxy's epic story. Their hungry growth is directly tied to how the starry galaxy develops around them. Whenever I watch them feed, devouring deep space gas, they blast out more raw energy than every single star in their host galaxy combined. This violent energy blasts away the raw gas needed to birth new stars, completely freezing stellar formation for millions of years. Put simply, these black holes do not just sit there like drain pipes. They actively regulate growth. They literally decide the final fate of galaxies. We call this process feedback. As you and I look out tonight, know those massive dark hearts are actively shaping the cosmos on an unimaginable scale. Through my lenses, I've watched plasma jets stretch for thousands of light years. They act like cosmic sculptors, reshaping deep space gas and dust across entire galaxies. I always find it somewhat ironic. The blackest objects in the cosmos, the anomalies that swallow light and evade our instruments, are the exact forces holding it all together. Dark matter, gravity, supermassive black holes, the silent builders of everything. And here we sit, orbiting a yellow star in a spiral galaxy, wrapped in a dark matter halo, circling a monstrous black hole we will never directly see. Every step you and I take, every breath we draw, happens in a universe gripped tightly by invisible hands. So the next time you join me in looking up at the night sky, remember this: the starlight we study is barely half the story. The rest, the hidden scaffolding, the silent astrophysics, that quiet gravity pulling it all together, is always there. It never shines, never speaks, just builds, always building. Our observatory photos make galaxies look incredibly serene, graceful spirals. Glowing halos and soft dust lanes, but make no mistake, deep space is never a quiet place. Out in that vast emptiness, I watch galaxies constantly moving, drifting, and orbiting. Gravity pulls them together like dancers in an endless waltz. Sometimes those cosmic dancers get just a bit too close. Their stellar arms entangle, their paths cross, and they simply collide. It does not happen with a bang. It is a slow, spectacular ballet unfolding over hundreds of millions, even billions of years. Yes, entire galaxies crash into one another, but before you picture exploding stars and planets smashing together like glass marbles, just breathe. What my colleagues and I see is far more poetic. Galaxies are mostly empty space. The stars are spaced out so vastly that even during a massive galactic collision, the odds of two suns actually striking one another are vanishingly small. It looks like watching two fog banks pass completely through one another. Except this fog is made of stars, deep space gas, and dark matter, all swirling within heavy gravitational fields. Even though individual stars survive the passing, the galaxies themselves are forever changed. When these two massive bodies meet, intense gravity violently pulls and stretches them. It warps their shapes into long, flowing tendrils of scattered stars. We astronomers call these tidal tails. They can stretch for hundreds of thousands of light years, looking exactly like glowing ribbons unraveling into the deep black. Each tail is a brilliant trail of stars flung outward by the passing. The interstellar gas clouds, however, are not nearly as lucky. When they hit, they smash together with absolute force, compressing, quickly heating, and triggering massive bursts of stellar birth. We call these starburst galaxies, and they can churn out new suns dozens or even hundreds of times faster than normal. It is a cosmic baby boom, ignited by the chaos of extreme gravitational upheaval. Some of the most stunning, chaotic galaxies I have ever cataloged are caught right mid-collision. Take the antennae galaxies. Through our lenses, these two merging spirals show long, curling arms of scattered stars and bright, brilliant pockets of heavy star formation. They give us a perfect snapshot of what happens when massive galaxies ignore personal space. Eventually, those two sprawling galaxies will settle into a single body, and that final product is rarely a spiral. Spiral structures are just too delicate, easily disrupted. After a major stellar merger, the result is almost always a giant elliptical galaxy. The orderly orbits of billions of stars get randomized. The gas, mostly burned up during the starburst phase or completely flung out into cold intergalactic space, is no longer thick enough to form those beautiful new arms. My research shows this is exactly how the largest galaxies in the known universe formed. Not from peaceful, quiet growth, but from slow-motion cosmic crashes, like cities built upon violently overlapping tectonic plates. But this is not just ancient astronomy. Our own Milky Way is not some passive observer here. Our home galaxy has its very own violent collisions to reckon with. As we speak, our galaxy is slowly merging with several smaller dwarf galaxies in our local group. I have tracked the Sagittarius dwarf galaxy being pulled apart and absorbed. Its ancient stars now trace ghostly, looping paths through the Milky Way halo. Other small celestial bodies follow similar paths. They are being digested, restructured, and firmly folded into our own. And then there is Andromeda. Let's examine our nearest massive neighbor, actively on a direct collision course with the Milky Way. Separated by 2.5 million light-years, we approach at 110 kilometers a second. That sounds terrifyingly fast, but from an astronomer's view, it is a remarkably slow and graceful approach. My models show the impact won't happen for another 4 billion years, but when it finally hits, the result will be undeniably spectacular. So, what happens to us? Surprisingly little, at least on the scale of our tiny solar system. Because the stars are spread so thin, direct hits are rare, but our entire night sky will change. Over millions of years, I imagine Andromeda growing larger and much brighter, eventually dominating the telescope's view entirely. The two galaxies will violently twist together, merge, and finally settle into a brand new shape, likely a giant elliptical galaxy. We astronomers lovingly call this future merger mela. Yes, really, even we scientists have our moments of whimsy, but long before that grand dance starts, collisions happen everywhere. I watch galaxies in dense clusters constantly interacting. Their shapes warp, their cosmic gas stirs. It is simply the life cycle of the cosmos. These star systems are not static islands. They evolve, grow, and transform through deep relationships, much like everything else in nature. What fascinates me most is that these interactions are not just destructive, they are profoundly creative. A merger can spark new star formation, feed hungry black holes, and completely reshuffle a galaxy to build entirely new, breathtaking structures. Like mixing two vivid colors of paint, the result is something entirely new, messy at first but always more vibrant. In this beautifully evolving cosmos we study, galactic collisions are not the exception. They are the rule. You and I might imagine the universe as calm and unchanging, a silent night sky sprinkled with eternally frozen stars. But I can assure you it is alive. Galaxies drift, fall into one another, and blend their light and stories. Even tonight, somewhere deep in the void, two galaxies begin their long, slow, gravitational dance. Someday they will finally collide, not in violence but in a quiet union, and a brand new galaxy will form. just as it always has been and always will be. For an astronomer, gazing into deep space means gazing back through time. It remains one of the quietest, most astonishing truths about our universe. Every single star shining in the dark night sky. Every distant galaxy my telescope captures shows us how it looked long ago. Light, for all its blistering speed, still takes a very long time to travel across space. And outer space is incredibly, impossibly vast, so when I look up from the observatory, I am quite literally time traveling. Take our sun. The warm sunlight touching your face during an afternoon walk left the solar surface about 8 minutes ago. That light is already 8 minutes old by the time it reaches Earth. You and I never see the sun as it is. We see it as it was, look past our own solar system, and that cosmic time delay only grows. The starlight from Alpha Centauri, our closest neighboring star system, is over 4 years old, and the glow of Andromeda, that is ancient light. It began its journey toward my lenses over 2.5 million years ago. Long before early humans, written language, or the wheel, that gentle shimmer is a memory, a quiet whisper from a past so impossibly distant it predates everything we know. But as astronomers, we go further. With the right tools, we peer back billions of years, almost to the dawn. The deeper I look into space, the further back in time I go. It is like peeling back layers of cosmic history, one single photon at a time. This is where my telescope becomes a time machine. Take the Hubble Space Telescope, for example. Launched in 1990, orbiting high above Earth, Hubble showed our team things we never imagined seeing. One of its greatest triumphs is the Hubble Deep Field. A beautifully simple idea, really. My colleagues pointed Hubble at a seemingly empty patch of sky, a section so entirely dark and blank it looked like nothing was out there. We let it stare for days, and when the data finally came down, that absolute nothingness revealed a vast sea of galaxies, thousands of them, each holding billions of stars, all packed into a speck of sky smaller than a grain of sand at arm's length. Some of those ancient galaxies were over 13 billion years old. I was staring deep into the past, almost to the very moment when the first galaxies formed. That light traveled for nearly the entire age of the universe just to reach my screen. It crossed unimaginable cosmic distances, past uncountable wonders, and finally landed on the mirror of Hubble, leaving behind a faint, beautiful trace. Today we operate an even more powerful time machine, the James Webb Space Telescope. Launched in 2021, Webb lets us see even deeper into the past. Not just because it is bigger, though its mirror is over 6 meters wide, but because it sees in infrared. That is the key, as space expands. The light from distant galaxies stretches out, much like pulling taffy, shifting into longer wavelengths. We call this process cosmic redshift. It means the very earliest galaxies now shine mostly in invisible infrared light. Hubble could only glimpse a fraction of that light. We built Webb to completely bathe in it. Already it shows my colleagues and me galaxies from just a few 100 million years after the Big Bang. Some are small, irregular, and chaotic, exactly as predicted. But others are surprisingly mature, like finding fully grown cities right after the first huts were built. For you and me, these discoveries are completely reshaping how we understand galaxy formation, maybe even rewriting cosmic history. Here is the most poetic part of my job: the farther away a galaxy sits, the younger it actually is. Yet it looks older to us in the observatory, because we are catching its light from billions of years ago. You and I are literally looking into the past tonight, and that is exactly how my field learns. I cannot just rewind the universe, but I really do not need to. Space has already sent its memories down to us, one photon at a time, and my colleagues and I catch them slowly, quietly, using massive glass mirrors, gold, and deep patience. Honestly, this is what astrophysics really comes down to. We are just listening to deep time with better and better instruments. Of course, even my best telescopes have their hard limits. There's a wall I cannot see past, the cosmic microwave background, the fading glow of the Big Bang. It is not that nothing existed before it, but the early cosmos was totally opaque. Before that moment, light simply could not travel. It was trapped, bouncing around like fog in a thick forest. Only after space cooled down and atoms formed did that light finally break free, starting its long journey to my lenses. That is our cosmic horizon, the absolute edge of visibility. Beyond that wall lies pure mystery, massive questions we astronomers are still trying to answer. But for now, our current data is extraordinary. Every image I pull from the Webb telescope, every frame from Hubble is a photograph of the past. A snapshot of a moment so far away it feels made up, but it is not. It is entirely real. That light touched something once, a star, a distant galaxy, a cloud of space dust. And tonight it finally touches my eye. So the next time you stare up at the night sky, remember you are not just looking up. You are looking back, way, way back. Those stars still shine for us, but many are beaming from a time when Earth was newly formed, when there were no astronomers to observe them, no catalogs to name them. And yet their ancient light persisted, crossing deep space and time just to reach us here tonight. Space does not just tell stories, it remembers them. We have searched so far. From the earliest whispers of matter to the massive sprawling spirals and glowing galactic cores. My colleagues and I have watched the cosmos light up, organize, and change. And bringing our telescopes back to the present, we find the universe is far from finished. Whole galaxies are still forming, merging, and slowly reaching toward one another across the empty void. Stick with me here because galaxies, much like us, rarely live alone. Instead, they gather, forming large groups, heavy clusters, and superclusters. These massive cosmic structures are so vast they defy imagination. Our own Milky Way is just one part of a gathering we call the local group. We map it as a quiet corner of space with over 50 galaxies, most being small and faint, little dwarf galaxies orbiting the heavier ones like tiny cosmic moons. The two largest members of our local galactic group are the Milky Way and our neighbor Andromeda. We are the twin giants of this quiet galactic suburb, slowly spiraling toward a massive collision. I have modeled our future merger many times, but currently, both galaxies keep a respectful distance, close enough to feel the gravity, but far enough not to bump elbows yet, and surrounding us are many smaller, fainter companion galaxies. Some, like the large and small Magellanic Clouds, I can easily observe from the southern hemisphere, watching them get pulled into our spiral arms. Other neighbors, like the Draco or Ursa Minor dwarf galaxies, are far more elusive. They are faint star collections barely keeping their shape as they slowly orbit right through our galaxy's invisible dark matter halo. Small groups like ours are common, but they are just the start. When I zoom my models out, I see galaxy clusters, huge collections of hundreds or thousands of galaxies, tightly bound by gravity. The Virgo cluster sits right past our local group. Through the lens, it is packed with beautiful spirals, heavy ellipticals, and every shape imaginable. Out there, galaxies are not politely distant. They crowd closely together, actively interact, and violently collide. Looking at the data, I can almost feel the tension. Massive gravitational tug-of-wars are happening across millions of light years. And these dense clusters sit inside even grander formations, giant superclusters. The Laniakea supercluster, our ultimate cosmic address, stretches over 500 million light-years across and holds about 100,000 entire galaxies. That is correct. Let us picture this together. 100,000 galaxies, each with billions of stars, drifting along a giant cosmic web we astronomers are just starting to map. And even that supercluster is just one tiny thread in the larger cosmic web, the vast, invisible structure forming the literal skeleton of our universe. Galaxies are not sprinkled randomly across deep space. Our maps prove they form distinct patterns, filaments, wide sheets, and dense nodes, like foam stretched across a dark sea. These massive shapes were seeded right after the Big Bang. For billions of years, they have been molded by the subtle push of dark matter and the endless, heavy pull of gravity. Between these bright filaments lie the voids, immense, quiet regions where almost no galaxies exist. Through my lens, I see cosmic voids millions of light-years wide, dark, silent. Only an occasional, lonely galaxy drifts through them, like a ship on a midnight sea. This stark contrast between dense galaxy clusters and empty space maps our modern universe. But here is the thing, not everything out there is still growing. Not everything rushes forward. When we astronomers study the cosmos, we see the grand dance slowing down, not in its speed, but in its creation. Many massive galaxies, especially those older ellipticals, just aren't forming stars anymore. They have burned through all the gas required for stellar birth. We actually call them red and dead, not because they are empty, but because their aging suns cast a soft red glow with no stellar nurseries left to replace them. Even our home, the Milky Way, makes fewer stars than it used to. It is certainly not finished yet, but that chaotic era of rapid star formation is long gone. We find ourselves in a much quieter chapter of galactic history. Meanwhile, the entire universe expands faster every day. It is driven by a force we still cannot fully explain: dark energy. This hidden pressure shoves distant galaxies apart from one another at terrifying, accelerating speeds. Trillions of years from now, any galaxy not anchored to us by gravity might just fade from our telescope sights entirely. Their ancient light will stretch out until it simply cannot reach Earth. Space will become much colder, quieter, and deeply isolated. But do not worry, we have plenty of time left. Right now, galaxies are still crashing together, changing and surprising astronomers. Through the lenses of Hubble, James Webb, and future space observatories, we can look deeper into the cosmos and further back in time. We are literally catching the echoes of galactic birth. We see ripples of massive collisions. We spot the faint glow of young stars whose light began traveling before Earth even had oceans. The night sky overflows with those ancient echoes. Every glowing dot tells a story. Some are just sparking to life, others burned out ages ago, but all of them build this beautifully vast cosmic architecture. The visible universe keeps painting itself right before our eyes. Galaxies are not just deep space mysteries, they are companions. Silent teachers, reminders that even in a cosmos so massive it breaks human comprehension, we belong to it and it belongs to us. Now, after tracing billions of years and endless light years, you and I have reached the end of tonight's journey. We have drifted from the initial spark of creation to the slow birth of galaxies. From the cosmic dark ages to that very first light, we watch stars flare awake, cluster into glowing cities, and spin through spirals guided by gravity. I have shown you galaxies colliding, merging, and fading into old age, quiet giants drifting through a living cosmos that never stops moving. We have wandered through the Milky Way, our very own galactic neighborhood, and felt the immense pull of black holes and dark matter, the silent architects behind everything we observe. And we have stared deep into the past. We caught ancient starlight that crossed the entire expanding universe just to meet our eyes tonight. It is truly humbling, is it not, knowing the stars above your roof are not just pinpricks of light but old memories. These galaxies are stories still unfolding. And knowing everything around you. Your hands, your very breath, the quiet thoughts in your head, they were all forged inside the core of a long-dead star. You are literally made of galaxy dust. You are part of this astronomical record. Maybe that is why the night sky feels so comforting, why our minds quiet down when we look up. Because some ancient piece of us still remembers what it feels like to drift through pure starlight. So now, as your eyes get heavy and your mind softens, I will ask you again, just like I did at the start, where on earth are you listening from tonight? What time is the clock showing there? Feel free to drop a note in the comments if you want. I genuinely love seeing where these observatory tours reach across the globe. It reminds me how deeply connected we are through wonder, curiosity, and literal stardust. If you enjoyed drifting through deep space with me tonight, maybe leave a like or subscribe for more sleepy astronomy. There is an entire infinite universe waiting out there. I would love to explore it alongside you. But for now, just rest. Let my telescope keep watch while the galaxies keep spinning, exactly as they always have. Good night, fellow space traveler. Your safe home among the stars.